Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. In my image transformation class, I discussed the concept of PCA, the Principal Component Analysis. So, how to reduce the dimension of the input vector. If I consider the feature vector, suppose x, I can reduce the dimension of the feature vector by neglecting the redundant information by PCA, the Principal Component Analysis. PCA finds the greatest variance of data. But one problem with the PCA is that it does not consider the class information. Suppose I have number of classes and the discrimination between the classes, that information is not considered by the PCA. So, for this I will consider another method, that is called the linear discriminant analysis. So, in case of the linear discriminant analysis, I can reduce the dimension of the input vector. Also, I can find the separation between the classes, that is the discrimination between the classes I can do. So, that concept I am going to discuss today, and also I discussed the concept of the Bayesian decision making, the Bayesian classifier, that is nothing but the generative model. So, what is the concept of the generative model? That means I have the information of the class conditional density, the probability of x given wj. So, that information is available, and with that information I can do the classification. So, I can determine the posterior density, the density is probability of wj given x I can determine. There is another classifier, that is called discriminative classifier. So, in this case the information of the class conditional density is not important. So, I can find the best decision boundary between the classes. Suppose if I consider two classes, I can find the best decision boundary between these two classes. So, for this I will discuss one algorithm, that is the support vector machine. So, today's class I will discuss these two concepts, one is the linear discriminant analysis and another one is the support vector machine. So, first let us consider the concept of the LDA and what are the problems with the PCA, that concept I am going to explain. So, in case of the PCA, if you know that I discussed in the image transformation class, I can reduce the dimension of the feature vector or the input vector, but in this case I am not considering the discrimination between the classes, that information is not available in the PCA. So, in this figure you can see I am considering n number of feature vectors and I am considering the m dimensional vector that I am considering. So, that means the dataset matrix X has a dimension of m cross n, and for this PCA the method is like this. First I have to subtract the mean from the original data, so that I will be getting a zero mean data set. So, I will be getting a zero mean data set, and after this I have to compute the covariance matrix. The covariance matrix I can compute like this, and from the covariance matrix I can determine the transformation matrix. So, for this I have to determine the eigenvectors and also I have the corresponding eigenvalues. So, this transformation matrix for the principal component analysis I can determine from the eigenvectors of the covariance matrix. So, you can see I can determine the eigenvalues and the eigenvectors I can determine from the covariance matrix, and from this I can determine the transformation matrix, that is the basis vector I will be getting, and I can consider the highest eigenvalue I can consider and the corresponding eigenvectors I can consider. So, that concept already I have explained in my PCA class, that is in the image transformation. But one problem of the PCA that already I have highlighted, that is the class discrimination information is not available. That is only I can reduce the dimension of the input vector, the input data or the input feature vector. So, in case of the LDA, the linear discriminant analysis, I can reduce the dimension of the data, the input data. So, reduce the dimensionality of a data set by finding a new set of variables smaller than the original set of variables. So, I can do this, and also I can retain most of the samples information. So, redundant information I can neglect, but I can retain most of the samples information. So unlike PCA, LDA uses the class information. So that information is available in case of the linear discriminant analysis, and I have to find a set of vectors that maximize the between class scatter while minimizing the within class scatter matrix. So that concept I am going to explain, because in case of the linear discriminant analysis, I have the class information and I have to find a set of vectors that maximize the between class scatter, and I can also minimize the within class scatter. So this mathematical concept I am going to explain in case of the LDA, the linear discriminant analysis. So LDA finds the new axis based on these two criteria. So one is the maximize the distance between the means of the classes. So I can consider suppose two classes. So I can maximize the distance between these classes. So that means I can find the maximum distance between the means of the classes, and also the minimize the variation within the class, that I can consider. So one is the maximize the distance between means of the classes, and also I can minimize the variation within the class. So I can consider this one, that means I have to minimize the variation within the class, and also I have to maximize the distance between the means of the classes. So this quantity I have to maximize. Now the question is PCA a good criterion for classification? Now in case of the PCA finds direction of greatest variance. Data variations determines the projection direction, but in case of the PCA, the class information is missing. We don't have the class information. But how? Actually we consider the eigenvectors. That means we want to find the directions of greatest variation. That means we can find the eigenvectors of the covariance matrix. But the class information is missing in case of the PCA. So let us consider what is the projection. In case of the PCA, we consider the eigenvectors, that is the direction of the projection. Now let us consider what is the good projection. Here in this figure you can see I am considering two classes. You can see one is the this class, another one is this class, the two classes. And I want to find the good projection. In case of the blue projection, if I consider the blue projection line, there may be overlapping of the samples of different classes. But if I consider this projection, that means these two classes will be well separated. In the first projection, if I consider the first projection, that is the blue projection, then in this case these two classes are not well separated. But in the second case, if I consider the second projection, if I consider this projection, the two classes are separated. So that means in case of the LDA, I have to see this condition, that is the separation between the classes. So for this, this information is important. One is the between class distance. So here again I am showing two classes. You can see. So this is the centroid of suppose class I, and this is the centroid of the another class MJ, that is the mean. Now in this case, the between class distance should be maximum. So you can see between these two means, one is Mi, another one is Mj. So one is Mi and another one is Mj. These two means I am considering. For two classes, the distance between the centroid of different classes should be maximum, that is between class distance. After this, I am considering another information, and that is within class distance. So that means it is the accumulated distance of an instance to the centroid of each class. So that means if I consider this is the centroid is Mi and the Mj, and you can see I am considering the sample points corresponding to the centroid Mi. So this within class distance should be minimum. So suppose distance between these samples and the centroid I can determine, and I can determine the accumulated distance. So that should be minimum, that corresponds to within class distance. So that means for the LDA, this is important. One is the between class distance, that is important. Distance between the centroid of different classes, that should be maximum. And within class distance, that means accumulated distance of an instance to the centroid of its class. So that should be a minimum. So these two condition, one is the within class distance, another one is the between class distance corresponding to LDA, that is very important. So in case of the linear discriminant analysis, LDA finds most discriminant projection by maximizing between class distance and minimizing within class distance. So here I am showing these two cases. First you can see I am considering this is the projection direction, that is the blue is the projection direction, and you can see the classes, the samples of the classes, two classes are overlapping. That is the discrimination between these two classes is minimum. But if I consider the second projection direction, that is the yellow, the discrimination between these two classes is maximum. So you can see the discrimination between these two classes is maximum. So I have to find that direction, in which direction the discrimination between these classes will be maximum. So that direction I have to estimate. So for this I have to consider these two cases, one is the within class distance, another one is the between class distance I have to consider. So that means I have to maximize between class distance and I have to minimize within class distance. So based on this I have to find the projection direction, and based on this projection direction I can find maximum separability between these two classes. Now I am considering two classes, it may be applicable for more than two classes also. So if I consider C number of classes, so this concept is also applicable. But in this example I am only considering two classes. So what is the mathematics behind the LDA that I want to explain? So let us consider a pattern classification problem, and for this I am considering C number of classes I am considering. So maybe the classes may be the fishes like the sea bass, tuna, salmon, like this I can consider number of classes, the C number of classes I can consider. And each classes has Ni samples. So m dimensional samples are available, and how many samples are available? Ni number of samples for each of the classes. And we have a set of m dimensional samples. So we have the set of m dimensional samples. So corresponding to the class is Wi. I have the samples x1, x2 like this. So we have Ni number of samples, and it is the m dimensional samples. And from this I can get a matrix, the matrix is X, that is stacking these samples from different classes into one matrix, that matrix is the X, and this each column of the matrix represent one sample. So I will be getting a matrix, the matrix is X from all the samples of different classes. Now I want to find a transformation of X to Y. X is the input data vector suppose. So I want to find a transformation of X to Y through projecting the samples in X onto a hyperplane with the dimension C minus 1. So I have to find the projection direction, that new data will be Y after the projection, and the objective is to get the maximum discrimination between the classes. So I have to find the best projection direction I have to find. For simplicity I am now considering only two classes suppose. So this principle can be extended for C number of classes. So first I am considering two classes. So we have the m dimensional samples. So we have the m dimensional samples, and we have the n number of samples. So n1 number of samples belong to the first class is W1, and n2 number of samples belonging to the another class is W2. And we seek to obtain a scalar Y by projecting the samples X onto a line. So in this case we are considering two number of classes, that means C is equal to 2. So that means C minus 1 means it is 2 minus 1, it is 1. So dimension is reduced to 1. And what I am getting, I am just doing the projection. Wt x, that is actually the dot product. If I consider the vector from, so it will be the dot product. So y will be the scalar. So Wt dot x, so W is the projection vector and x is the input vector that I am considering. So if I take the dot product between Wt and x, so I will be getting the scalar is y. In the figure you can see I am showing a projection direction, the direction is this, one projection direction you can see, and in this case also I am considering two classes, and here I am considering two-dimensional samples because I am considering x1 and x2, that this is a two-dimensional samples. So corresponding to this you can see the separation between the classes is minimum because there is a overlapping between the samples of the classes, the two classes. But if I consider in the second figure, I am considering a projection direction, you can see I am getting the separation between the classes, between the samples of the two classes. So that means the second projection direction is better as compared to the first projection direction. So I have to find which one is the best projection direction. So that is the objective of the LDA. So in order to find a good projection vector, we need to define a measure of separation between the projections because I am getting the projection is nothing but y, that is nothing but Wt dot x. So I am getting the scalar y. So first the mean vector of each class in x and y feature space I can determine. So mu I can determine because I have ni number of samples. So I can determine the mean of x corresponding to a particular class, and you can see I can also determine the mean of the projected data. So y is the projected data. So mu I tilde that I can determine. So it will be something like this, 1 by ni summation xt x. So it is mu I tilde I can also determine. So you can see it is 1 by ni Wt x, and after this just you do this mathematics. So I can determine the mean of the projected data. Now I am considering the objective function. The objective function is jw, and the main objective or the main goal is to find the maximum distance between the projected means, so that I will be getting maximum separation between the classes. So objective function jw I am considering, and this is the mu1 is the projected mean for the class 1 and mu2 is the projected mean for the class 2. So I am considering mu1 tilde and mu2 tilde, that is the projected mean. So from this you can determine this, from the previous equation you can determine this. Now in this case you can see the distance between the projected mean is not a very good measure because it does not take into account the standard deviation within the class. So that information is not considered in this case because we considered the distance between the projected mean, and that may not be a good measure because in this case we are not considering the standard deviation within the class. So that information we are not considering. So pictorially that concept I am showing here. Here you can see the axis has a larger distance between the means in the first case, but in this case it is not a good separability. There may be some overlapping between the classes. But if I consider the second case, this axis gives better class separability. So you can see if I consider this axis, that is this projection direction, then I will be getting maximum separability between the classes. But in the first case I will be getting the larger distance between the mean, but in this case the separability is not good. The separability between the classes is not good as compared to the second case. In the second case I am getting better class separability. So that is the solution of this problem is given by Fisher. So that is why this method is called Fisher linear discriminant analysis. So what is the solution of this problem? The solution of this problem is to maximize a function that represents the difference between the means normalized by a measure of within class variability. So that means I am considering the information or the measure of the within class variability, and I can consider as a scatter. For each class we define the scatter and equivalent to the variance. So I can consider that this is the scatter and it is equivalent of the variance. That is the sum of square differences between the projected samples and their class mean. So that I am considering. The sum of square differences between the projected samples and their class mean I am considering. So Si tilde square measures the variability within the class Wi after projecting it onto the Y space. So Y space means it is the projected space. So Si tilde square means it is a measure of the variability within the class is Wi. So that means if I consider this one, S1 tilde whole square plus S2 tilde whole square, that gives the measure of the variability within the two classes after the projection. So that is called the within class scatter of the projected sample. That means I am considering S1 tilde square plus S2 tilde square that measures the variability within the two classes after the projection, and it is called the within class scatter of the projected samples. So in case of the Fisher linear discriminant function, we define a linear function. The linear function is Wt.x, Wtx, that maximize the criterion function. What is the criterion function? The distance between the projected means normalized by the within class scatter of the projected samples. So I am considering this the criterion function Jw I am considering. So the objective is to maximize the criterion function. I have to maximize this. That means the distance between the projected means normalized by the within class scatter of the projected samples I have to maximize. So that is the criterion function I am considering in case of the Fisher linear discriminant. That means in case of the LDA, what actually we are considering? We are looking for a projection where the samples of the same class are projected very close to each other, and at the same time the projected means are further apart as far as possible. So that is I am considering. So one is within class distance, another one is the between class distance, that is I am considering, and based on this I am determining the projection direction. So this concept I am showing here again. So that means the maximum separation between the classes, but samples from the same class are projected very close to each other. So that I am also considering. In order to find the optimum projection W star, we need to express Jw as an explicit function of W. So I have to find that Jw, that is the criterion function. So for this we are defining a measure of the scatter in multivariate Fisher space X, which is denoted as scatter matrix. So I am considering Si. So Si is the covariance matrix of the class Wi, and Sw is called the within class scatter matrix. So I can determine the within class scatter matrix from S1 and S2. So S1 is the covariance matrix of the class 1 and S2 is the covariance matrix of the class 2. So from this I can determine Sw, that is nothing but within class scatter matrix. This is important for considering this criterion function. So Jw I am considering. Now the scatter of the projection Y can be expressed as a function of the scatter matrix in Fisher space X. So here you can see I am considering the projected data. So Si tilde square, that I can determine. So Y is the projected data, and you know what is mu I tilde, you know. So from this you can determine this one, just you can see this one. And similarly you can also determine the S2, S1 and S2, that is the S1 tilde square and S2 tilde square, that you can determine, and that is nothing but Sw. So Sw tilde is the within class scatter matrix of the projected sample Y. So you can see the mathematics and this derivation you can see. So this is a very simple derivation, and based on this you can see, because I am considering the projected means, the projected mean is mu1 tilde and the mu2 tilde. So the separation between these two means, that is the projected mean, should be maximum. So just I am determining this Wt mu1, that corresponds to mu1 tilde, and mu2 tilde is nothing but Wt mu2. So you know this expression, and from this you can see I am getting SB tilde. So SB is nothing but the between class scatter matrix. So you can see how to determine the within class scatter matrix SW, and also we can determine the between class scatter matrix SB. So SB is the between class scatter of the original samples, and what is SB tilde? That is the between class scatter of the projected sample Y, that you can determine. And after this, this Fisher criterion function, that is JW, can be expressed in terms of the between class scatter matrix and the within class scatter matrix, that can be represented like this. So JW is nothing but WT SBW divided by WT SWW. So it can be represented like this. So JW is a measure of the difference between class means, that is encoded in the between class scatter matrix, normalized by a measure of within class scatter matrix. So here you can see, so it is the between class scatter matrix, and it is normalized by a measure of the within class scatter matrix. So that is the SW, and I have to maximize this criterion function JW. So that is why I am taking the differentiation with respect to W. So W is the projection vector. So I have to maximize JW with respect to W. So that is why I am doing the differentiation. You can see this mathematics. So how to do the differentiation? By using the Sein rule. So you can do the differentiation by using the Sein rule, and since I have to find the maximum value, so that is why I am equating it to 0. So I have to find the maximum of JW. After doing all this mathematics, I will be getting this one. So you see this mathematics, mainly just I am applying the differentiation, applying the Sein rule, and just equating it to 0, because I have to find the maximum of JW. So it is nothing but the solving the generalized eigenvalue problem. So SW minus 1, that is the inverse of the within class scatter matrix, into SB, the between class scatter matrix, and W is the projection vector, lambda W. So lambda is the eigen values. So lambda is the scalar. So corresponding to this, if I consider this eigenvalue problem, I can determine the vector W, that I can determine, that is the projection vector I can determine. So this W star I can determine, that is nothing but SW inverse mu1 minus mu2. So here you can see I am determining the best projection direction, the optimum projection direction W star. So this is known as Fisher's linear discriminant. And if I consider the same notation as PCA, the solution will be the eigenvectors of Sx, because in case of the PCA also we determine the eigenvectors of the covariance matrix. So similarly, the solution will be the eigenvectors of the Sx. So that is nothing but SW to the power minus 1 into SB. So this is the very similar to the PCA, the principal component analysis. In PCA, we considered the eigenvectors of the covariance matrix. In this case, you can see I am considering SW to the power minus 1 into SB. So one is the within class scatter matrix, another one is the between class scatter matrix. So I am considering one numerical example. So how to apply the LDA for two classes. So I am considering samples of the class W1. So I am considering two classes, W1 and W2. And I am considering the samples for the class W1. So these are the samples. The samples are two-dimensional. And similarly, I am considering the samples of the class W2, that is also two-dimensional. And I am showing the MATLAB code for this. And I am considering the samples x1 and x2 corresponding to the classes W1 and W2 respectively. And you can see you can plot the samples corresponding to these two classes. One is the green sample, you can see the green colored sample, and another one is the blue colored samples. After this, the class means I can determine by using this expression. So corresponding to the class W1, I can determine the mean of the samples, and similarly corresponding to the second class also I can determine the class mean, so that I can determine. And in the MATLAB, you can write like this. You can determine the mean of x1 and also mean of x2 you can determine. After this, the covariance matrix of the first class also you can determine. That is nothing but S1. So S1 you can determine, that is nothing but the covariance matrix of the first class. And in a MATLAB, you have to write simply the covariance of x1. So you can write like this. So you can determine S1. And similarly, you can determine the covariance matrix of the second class. So S2 is the covariance matrix of the second class you can determine. And in the MATLAB, S2 is equal to covariance x2, that you can determine. And from this S1 and S2 you can determine within class scatter matrix SW you can determine. That is the within class scatter matrix you can determine from S1 and S2. So you will be getting this. And after this, you can also determine the between class scatter matrix from these two means, because already you have calculated mu1 and mu2. So from mu1 and mu2 you can determine between class scatter matrix. So you can see, so I am computing the between class scatter matrix, and even in the MATLAB also it is very simple. So you can determine between class scatter matrix. After this, the problem is the eigenvalue problem that you have to solve. So the eigenvalue problem is this. So lambda is the eigenvalue. So this eigenvalue problem you can solve like this, and I will be getting two eigenvalues, lambda 1 and lambda 2. So lambda 1 is 0 and lambda 2 is 12.2007. So you will be getting two eigenvalues. This is nothing but the solution of the generalized eigenvalue problem. So you can solve this problem. And after this, I can determine the vector W. So you can determine W1 and W2 you can determine. So we can compute the LDA projection. So it is nothing but in the MATLAB you can do like this. So you have to find the inverse of SW, and I will be getting the projection vector. W is the projection vector. So I will be getting W1 and W2. And which one is the optimum projection direction corresponding to LDA? That is the W2 is the optimum projection direction that I can determine, which gives maximum JW. So this W2 is the optimum projection vector that I can determine because it gives maximum JW. Or maybe directly we can compute like this. The optimum projection direction or the vector I can determine like this. So SW minus 1, that is nothing but the inverse of the within class scatter matrix, mu1 minus mu2. So from this you can determine the optimum projection vector that you can determine. So this is one example. This LDA you can apply for C number of classes. So in the book you can get this information how to apply the LDA for C number of classes. But in my discussion I only considered 2 classes. So how to apply the LDA for 2 classes? For this you have to determine SW and the SB. One is the within class scatter matrix, another one is the between class scatter matrix. And here you can see I am showing one projection direction corresponding to smallest eigenvalue. So smallest eigenvalue I am considering, and I am showing the projection direction. And in this case, if I consider the PDF of the classes, they are not well separated. That means there is no discrimination between the classes corresponding to this projection direction. In case of the PC also, we considered the eigenvalues and the corresponding eigenvectors. So in case of the PCA, we consider the highest eigenvalue and corresponding eigenvectors that we considered. And if I consider the smallest eigenvalue, that corresponds to the redundant information or maybe the noise that we can neglect in case of the PCA. Here in case of the LDA, what I am considering, the smallest eigenvalue I am considering, and corresponding to this I can determine the projection direction. And here you can see corresponding to the smallest eigenvalue, the separation between the 2 classes is not maximum, it is overlapping of the PDF of the classes. That is the bad separability. But if I consider the highest eigenvalue and corresponding to this I can determine the projection direction, in this case you can get the good separability between the classes. So you can see I am showing the PDF of the classes, and you can find the good separability between the classes corresponding to the highest eigenvalue you can see. Now, in case of the PCA, we have seen how to recognize a particular phase. The phase recognition using PCA, that concept already I have explained. That means any phase can be expressed as a linear combination of eigenphases. So, you can see I am considering the eigenphases like this. So, in my class I have explained how to determine the eigenphases, and the any phase can be represented by a linear combination of the eigenphases. Similarly, in case of the LDA, any phase can be represented by a linear combination of Fisher phases. In case of the PCA, we consider the eigenphases, but in this LDA, we are considering Fisher phases. So, that means the any phase can be represented by linear combination of Fisher phases. So, that concept I am going to explain now. So, how to recognize a particular phase? Suppose we have C number of classes. This mu I can determine, that is the mean vector of the class I can determine. So, I have C number of classes. So, and also I am considering mi number of samples for the classes within a particular class. So, from this I can determine that what is the total number of samples. The total number of sample is m is equal to summation over 0 to C mi. So, mi be the number of samples within class I that I am considering, and from this I can determine total number of samples I can determine. And I have already explained, I can determine the within class scatter matrix, and also I can determine the between class scatter matrix from the input samples. After this I am considering the criterion function, that function I am considering. So, what is the condition? I have to maximize the between class scatter, but I have to minimize the within class scatter. That is the condition, because I have to find the best projection direction I have to find. So, for this what I have to do? I have to maximize the between class scatter, and also I have to minimize the within class scatter. So, such a transformation should retain class separability while reducing the variation due to source other than the identity. So, maybe the variation may be the illumination variation I may consider, but the main important point is the class separability. So, we have to find the class separability, that is the maximum discrimination between the classes I have to find. And already I have explained that is nothing but the eigenvalue problem. So, this solution is something like this, and I will be getting the Fisher phases I will be getting if I consider the eigenvectors of SW to the power minus 1 into SB. So, I will be getting the eigenvectors, that is nothing but the Fisher spaces. That means you can see the projected data can be represented by a linear combination of the Fisher phases. So, here you can see I am considering the U is the transformation matrix, and how it is obtained? It is nothing but the eigenvectors I am considering, the eigenvectors of SW to the power minus 1 into SB. So, eigenvectors I am considering, and based on this eigenvector I can construct the transformation matrix. So, X is the input data minus mu, that is the mean is subtracted from the input data, that means the input data is normalized, and after this I am considering the transformation. The transformation is the B is equal to ut x minus mu. So, suppose in case of the KL transformation, what I have considered, y is equal to a x minus mu x, I considered like this. Similarly, in this case I am considering the U is the transformation matrix, y is this, and x minus mu x like this I am considering. So, this U is the transformation matrix, and this transformation matrix I can obtain from the eigenvectors of SW minus 1, that is the inverse of the within class scatter matrix into SB. So, I can get this one, this one U. That means any phase can be represented by a linear combination of the Fisher phases. So, the procedure for the phase recognition is very similar to the phase recognition by PCA. First, I have to do the normalization of the input data. That means from the original phase, the mean phase is subtracted. After this, I have to determine the Fisher phase. I have to determine, and that means I am considering the weights. The weights are W1, W2, W3 like this. that I have already explained in the PCA. So that means any unknown phase can be represented by a linear combination of Fisher phases. And suppose a new phase is coming, so a new phase can be also represented by a linear combination of Fisher phases. After this, what I have to do for recognition? Just I have to compare the weights. So just I have to compare the weights. One is the weight corresponding to the training, and another one is the weights corresponding to the input test phase. So I have to compare the weights, and based on this comparison, if it is less than a particular threshold, so based on this condition I can recognize a particular phase. So this concept is very much similar to the phase recognition by PCA, but in this case what I am considering, I am considering the Fisher phase. I am considering, corresponding to this I am determining the transformation matrix. The transformation matrix is U, that is obtained from the eigenvectors. The eigenvectors of SW to the power minus 1 SB. In case of the PCA, we consider the transformation matrix A. The transformation matrix is obtained from the eigenvectors of the covariance matrix of the input data. So Cx is the covariance matrix of the input data, and I am determining the eigenvectors, and from the eigenvectors I can determine the transformation matrix. In case of the LDA, what I am considering? I am again considering the eigenvectors of this SW to the power minus 1 into SB, and from this I can determine the transformation matrix. The transformation matrix is U. So these two concepts are very similar, the phase recognition by PCA and the phase recognition by LDA. Now next I will discuss the concept of the support vector machine. Now I will discuss the concept of support vector machine and introduction of support vector machine. So briefly I will explain the concept of the support vector machine. So what is support vector machine? So support vector machine is a classifier derived from statistical learning theory, and already I have explained it is the discriminative model, because in this case I do not need the information of class conditional density. So I have to determine the best decision boundary between two classes. So if I consider more number of classes, I have to find the best decision boundaries between the classes. So that is why it is called a discriminative classifier, because I do not need the information of the class conditional density. And support vector machine, we can consider different applications like handwriting character recognition, that is one applications, and there are many other applications like object detection and recognition, content based image retrieval, text recognition, biometrics, speech recognition. So there are many applications of support vector machine which can be used for classification and recognition. So for this we may consider handcrafted features for classification. So like this already I have explained some handcrafted features like color feature, texture features, or maybe the hog shift I can consider, and based on these handcrafted features I can do the classification by support vector machine. So you know this condition, that is the discriminate function, you know. So already I have explained about the discriminate function. Now this Fisher vector x can be assigned to a particular class. The particular class is Wi. Based on this condition, the condition is if Gix is greater than Gjx and j is not equal to I. So corresponding to this I can assign a Fisher vector x to the class is Wi. This is based on the discriminate function. And if I consider two classes, that is the two category case, so I can determine G1x and also I can determine G2x. So G1x minus G2x, that is nothing but Gx. Suppose Gx is equal to 0, that corresponds to the decision boundary, that already I have explained. So Gx is equal to 0 means it is the decision boundary. In the decision boundary, G1x is equal to G2x. So x is the Fisher vector. So based on Gx, I can take a classification decision. So I can consider or I can decide the class W1 if Gx is greater than 0. Otherwise, I have to consider the class is W2. And for the minimum error rate classifier, that already I have explained. So Gx can be represented like this. So Gx is nothing but G1x minus G2x. So what is G1x? That is nothing but P, the probability of W1 given x. That is the posterior probability. And similarly for G2x, the posterior probability is probability of W2 given x. So for each and every class, I have to determine Gx, and I have to find the maximum discriminant function, and based on this I can take a classification decision. And here I have shown some decision boundaries. You can see first I am considering the nearest neighbor classification. So you may get a decision boundary like this. So this is the decision boundary between two classes, and in case of the decision tree, this is nothing but the binary decision, either yes or no. So that type of decision I can consider by considering the decision tree, and corresponding to this I may get the decision boundary like this. That is the binary classification type classifier. And if I consider the Gx is a linear function, so suppose Gx is equal to Wt, that is the transpose x plus b. So W is the weight vector and x is the input feature vector plus b is the bias. So corresponding to this, if I consider a linear function, then in this case I will be getting a linear decision boundary like this. And also I may get the nonlinear decision boundary between the classes. So the last example is the nonlinear function, that is the nonlinear decision boundary I can get. So this is about the decision boundaries. So I am now considering the discriminant function. The discriminant function is Gx, that is equal to W transpose x plus b. So now Gx is a linear function, that is the linear discriminant function I am considering. So Gx is equal to Wt x plus b, and I am considering a hyperplane, that is the decision boundary between two classes. You can see here I am considering a two-dimensional Fisher space. You can see x1 and x2, that is the two-dimensional Fisher space I am considering, and you can see this is the decision boundary. So I am considering the decision boundary like this, decision boundary between the classes. So it is Wt x plus b is equal to 0. So that is the equation of the decision boundary. And suppose Wt x plus b is greater than 0, that corresponds to the class. Suppose the class is W1, this class. And if Wt x plus b less than 0, that we have to consider the class is W2. So these two class I can consider. One is the W1, another one is the W2. This W is different, this is the weight vector. So W1 and W2 I am considering as classes, two classes I am considering. And unit normal, that is the unit length normal vector of the hyperplane also I can determine. So if you see this vector is the unit vector, that is the unit length normal vector of the hyperplane I can determine, that is nothing but W divided by the norm of W. So that unit vector also you can determine. Now how will you classify these sample points using a linear discriminant function in order to minimize the error rate? So that is the concept. So I am considering two classes. So the first class is denoted by +1 and second class is denoted by -1, and it is a two-dimensional Fisher space I am considering. So infinite number of answers because I have to minimize the error rate, and you can see I am showing the decision boundary between these two classes. Again I may consider another decision boundary between these two classes, or I may consider another decision boundary between these two classes, or I may consider this decision boundary between these classes. So I may get the number of decision boundaries, but which one is the best decision boundary, that I have to determine in the support vector machine. So which one is the best decision boundary between these two classes, that I have to determine by considering some optimization criterion that I am going to explain in my next slide. So the linear discriminant function or the classifier with the maximum margin is the best. So this is the definition of the best decision boundary. So what is the definition of the margin, that you can see here. So margin is defined as the width that the boundary could be increased by before hitting a data point. So you can see I am considering the boundary like this, and I am increasing the width of the boundary, and so that it will just touch the sample points. That means you can see the vector, these are the sample points. So before hitting the data points, I can stop. So based on this, I can define the margin of this, the hyperplane. So this is the definition of the margin. So beyond this, I cannot increase the width because it will touch the data points. So just before the hitting the data points, I have to stop, and corresponding to this, if I consider this is the width of the decision boundary, suppose, that corresponds to the margin. So which is the best decision boundary I want to determine, because in my previous slide I have shown I can draw number of decision boundaries between these two classes, but which one is the best, that I can determine based on the margin. If the margin is more, then that will be good. That means for a good decision boundary, the margin should be more or margin should be high. So that based on this margin condition, I can find the best decision boundary between the classes. The best decision boundary means it is robust to outliers and thus strong generalization ability. So here you can see I am considering the safe zone, because beyond this I cannot increase the margin because it will touch the data points. So that corresponds to the safe zone. So this is the safe zone I am getting based on the margin. So how to determine the best decision boundary? That means how to maximize the margin between the classes. So suppose the large margin linear classifier that I want to design, that means the margin should be the maximum, and already I have mentioned. So I have two classes, one is the plus, another one is plus 1, another one is minus 1. So given the data points, I have the data points xi, yi like this, I is equal to 1 to n, and for the class, that is yi is equal to plus 1. So corresponding to this, wt xi plus b should be greater than 0, and similarly for the second class yi is equal to minus 1, wt xi plus b should be less than 0. So these are the conditions, and after this I can do some scale transformation for both w and the b, and corresponding to this, these two equations will be equivalent to this. So yi is equal to plus 1, that corresponds to wt xi plus b greater than equal to 1, and for yi is equal to minus 1, wt xi plus b should be less than equal to minus 1. So I will be getting these two new conditions. So these two new conditions I am obtaining after the scale transformation on both w and b. So you can see in this figure I am considering the data points. So if you see in the next figure, here you can see I am considering x plus and the x minus. So this is the x plus, this is the x plus, and this is the x minus. That means the margin is about to touch the data points. So in one side it is x plus, in another side it is x minus. So this x plus and the x minus, they are called the support vectors, because this margin is about to touch the data points. Beyond this I cannot increase the width of the margin. And what is the objective? My objective is to get the large margin linear classifier. So I have to get the maximum width of the margin. So that is my objective, that is my goal. And based on this I am defining the support vectors. The support vectors are x plus and the x minus. So x plus corresponding to the class w1, suppose, and another one is x minus corresponding to the class w2. So I have these support vectors. So with the help of these support vectors I can define the margin. So here you can see these are the support vectors, x plus and the x minus, these are the support vectors. So we know this condition, the wt x plus b is equal to 1 corresponding to the first class. So I am now considering the support vector. So in this equation wt x plus is the support vector I am considering, plus b is equal to 1, that I am considering, and again I am considering wt x minus. So that x minus support vector I am considering, plus b is equal to minus 1. So these two equations I am considering for two classes. The classes are W1 and W2. And now I want to determine the width of the margin. So the margin width can be determined like this: M is equal to x plus minus x minus. So this is one support vector and x minus is another support vector, and I am considering the normal to the hyperplane. So you get this unit normal to the hyperplane I am considering. So this unit normal already I have determined. So this is the unit normal, that is the n, and this is nothing but it is equal to 2 divided by W norm. So I am just determining the norm of W. W is the weight vector. Now for the large margin linear classifier, what I am considering? I am considering the formulation that I have to maximize the margin. So the width of the margin is 2 divided by the W norm. So I have to maximize this. That is the goal of the large margin linear classifier in the support vector machine. And based on this, what are the conditions? The condition is yi is equal to plus 1. For this condition, the condition is Wt xi plus b greater than equal to 1. And what is the another class? The another class is yi is equal to minus 1. That is the another class. And this condition is Wt xi plus b less than equal to minus 1. And again the formulation, I have to maximize 2 divided by W norm, that is equivalent to minimizing 1 divided by 2 W norm whole square. So this is actually equivalent to this. The maximizing 2 divided by W norm is equivalent to minimizing 1 by 2 W norm whole square, such that these two conditions I have to consider. So formulation is this. So minimize 1 by 2 W norm whole square, that I have to minimize, and condition is this. So here I am considering this optimization problem. So I have to minimize this subject to the condition is this. So this is a optimization problem. So how to solve this optimization problem? So for solving the optimization problem, I can consider Lagrangian function. So in mathematical optimization, Lagrangian multiplier method is used. You know that condition. So you have to see the mathematics book. In mathematical optimization, Lagrangian multiplier method is used, and it is used to find local maxima and the minima of a function subject to some constraints. That means subject to the condition that one or more equation have to be satisfied exactly by the chosen value of the variables. So I am repeating this. It is used to find the local maxima and the minima of a function subject to some constraints. That means subject to the condition that one or more equations have to be satisfied exactly by the chosen value of the variables. In order to find the maximum or the minimum of a function, suppose the function is fx. So I want to find the maxima or the minima of a function fx subject to the equating constraint. So constraint is suppose gx is equal to 0. So this constraint I am considering. Then this Lagrangian function I can write like this. This is a Lagrangian function x lambda. So lambda is the Lagrange's multiplier, is equal to fx minus lambda gx. So I can write like this. So for more details, you have to see the mathematics books. So how to do the optimization by considering the Lagrange's function. So this is the Lagrange's function, and I have to minimize this one. So alpha I is the Lagrange's multiplier. So this is the Lagrange's multiplier. So again I am writing this. So I have to minimize this function, the Lagrangian function, and subject to the condition is alpha I should be greater than equal to 0. So alpha I is the Lagrangian's multiplier. And for this I am just taking the derivative of LP with respect to the weight vector. The weight vector is W, and similarly the del LP divided by del B should be equal to 0. So based on this differentiation, I want to find the maximum or the minimum conditions. So based on this the partial derivative, I want to find the value of W and this. And this is nothing but the Lagrangian dual problem. That means you can see, because my objective is to minimize this function, the Lagrangian function, subject to the condition, this condition is important, that is equivalent to maximizing this, subject to this these two conditions, and this is called the Lagrangian dual problem. So you see the mathematics, again I am repeating this, you see the mathematics how to solve the optimization problem using the Lagrangian function. And now I am considering the KKT condition. What is the KKT condition? So I am considering, so from the KKT condition is nothing but, the KKT means Kruskal-Tusker condition, that also you have to see, that is called the KKT. It is used in mathematical optimization. It is nothing but the first derivative test. It is also called the first order necessary condition for a solution in a nonlinear programming to be optimal, provided that some regularity conditions are satisfied. So this is the briefly what is the KKT. So it is used in mathematical optimization, and it is nothing but the first derivative test, and it is also called the first order necessary conditions for a solution in a nonlinear programming to be optimal, provided that some regularity conditions should be satisfied. So by considering this KKT, I am considering this one, that is alpha I into yi, and after this I am considering Wt xi plus b minus 1 is equal to 0, that I am considering, and thus only for the support vector, that is alpha I is not equal to 0, that is only support vector have this condition, that is alpha I is not equal to 0. So the solution will be like this. So I will be getting the solution of this. So I will be getting the value of W, and also I have to consider this one, get B from this. So I can get B from this equation, and in this case xi is the support vector. So I am considering xi is the support vector, and in the figure also I have shown the support vectors, and you can see this is the margin I am considering. So x plus and the x minus, these are the support vectors, and based on this, you can see based on this Lagrangian multiplier function, Lagrangian function, I am getting the solution, and you can apply the KKT, this condition, and I will be getting the value of W, and also I can get the value of B. The B also I can determine from this. And finally the linear discriminant function I will be getting like this, Wt into x plus b is nothing but I will be getting this one, and only I am considering the support vector. I is mainly the support vector I am considering. So alpha I is nothing but it is the Lagrangian multiplier. So I is nothing but the support vector. So you can see in this expression, in the Gx expression, that is the discriminant function, the linear discriminant function. So it is nothing but the dot product between the test point. So test point is x, and the support vectors are xi. So first I have to determine the dot product between the test point x and the support vectors xi, and based on this I can determine Gx. So suppose the test vector is coming, suppose new test vector is coming. So for this what I have to do, I have to find the dot product between the test point x and the support vector xi, and from this I can determine the discriminant function. The discriminant function is Gx. Also keep in mind that solving the optimization problem involved computing the dot product between xit and the xj between all pairs of the training points. So for all pairs of the training points I have to find the dot products. That is the condition. So based on this this discriminant function, I can do the classification by considering the support vectors. And suppose if I consider, if the data is not linearly separable, so suppose if I consider the noisy data points or the outliers, and again here I am showing two classes, one is the plus, the green, another one is the white, that is the minus, two classes I am considering, and I am considering the noisy data points and the outliers. So for this, what is the formulation? The formulation is I have to consider slack variables. So slack variable I am considering, so can be added to allow misclassification of difficult or the noisy data points. These slack variables are introduced to allow certain constraints to be violated. So slack variables are defined to transform an inequality expression into an equality expression. That is the mathematics you can see. That is the slack variables we can define to transform an inequality expression into an equality expression. So that is the objective of the slack variables. And you can see I am showing these equations. WTX plus B is equal to 1. Corresponding to this is the line. WTX plus B is equal to 0. That is the decision boundary. WTX plus B is equal to minus 1. That is the line. And you can see the margin here. I am showing the margin here. And corresponding to this slack variable problem, the formulation will be something like this: 1 by 2 W norm whole square, and after this plus C. So C parameter I am considering, and this is the slack variable. So eta I is the slack variable. So the conditions are like this. So I have to consider these two conditions, and this parameter C can be viewed as a way to control overfitting. That means the parameter C tells the optimization how much you want to avoid misclassification by each training examples. So that means I have to avoid the misclassification, and this parameter C controls the overfitting. So that information I am giving with the help of the parameter. The parameter is C. So this is the concept of the large margin linear classifier. So briefly I have explained the large margin linear classifier. And also there are the nonlinear support vector machines. Suppose if I consider many noisy points or the outliers, so for this I can consider nonlinear support vector machine, and in this case I can consider the projection of the low dimensional data into high dimensional space. That means I can do the projection of the low dimensional space into high dimensional space, and I can consider the nonlinear support vector machine. I am not explaining the concept of the nonlinear support vector machine. That briefly I have explained the concept of the support vector machine, that is the large margin linear classifier. In this class I discussed the basic concept of the LDA and the support vector machine. In case of the LDA, I have to find the best direction of the projection. So which one is the best projection direction I have to find, and for this I have considered one criterion function, and for this I considered between class scatter matrix and the within class scatter matrix. So based on this I can find the best projection direction I can find. In case of the support vector machine, I determine the best decision boundary between two classes. So that means I have to maximize the margin between the two classes, and in this case based on this the margin, the width of the margin, I can define the support vectors, and based on the support vectors I can determine the discriminant function Gx, and after this I can do the classification. The support vector machine is a discriminative classifier because I do not need the information of class conditional density. So these concepts, two concepts, one is the LDA, another one is the support vector machine. Briefly I have explained in this class. So let me stop here today. Thank you.